Hi everyone, my name is Akihiro Hayashi. I'm a senior research scientist at Georgia Tech, and so before diving into details, so I'm just gonna introduce the authors. And again, so I'm a senior research scientist at Georgia Tech, and I actually joined the Habanel group as a postdoc back in the 2013, and I've been here like over 10 years. And Shubu is a PhD student, and he joined Habanel group at 2023. And Youssef, actually, he's here, and he joined the group back in the 2022, and Jiawei is a research scientist who joined the Habanel group since 2012. And yeah, these are authors, and let's dive into more detail. So just a recap of the very classic BSP model where you can maybe imagine the MPI or OpenSHMEM like programming model where you have the pair of the memory and the processor, and essentially you have a set of that pair memory processor, and each CPU memory first do the local computation, which is the blue part of this picture. So there's no communication. You do some very, very local operation. But at some point you start doing some communication between them, and then you do the global barrier, and you iterate this process until you get something interesting. And we are sort of thinking about extending this retention model by adding some flavor of the asynchronous active messages, and where you can still do the very basic BSP-like operation, like again, CPU do this just local computation, but at some point you can create some active message and send it to some remote PE and asynchronously, and so that you can do something very interesting. And here, this is one solution to the data movement problem, where instead of getting data from memory, we're just gonna move the compute to data to the more efficient processing. And we call it the FA-BSP model, fine-grained asynchronous synchronous parallel model, and in short, the FA-BSP. And we actually realized that this is very, very useful, particularly for writing the irregular applications, such as a graph algorithm or something like that. And this is more like a very, very rough summary of the FA-BSP execution. So in a nutshell, the FA-BSP is some PGAS memory space plus actor-based asynchronous messaging, and plus the very original BSP model. And here, actor is actually single-threaded. You can imagine that this PE actually is executed on a single CPU core, and in which there's some actor, and the actor has you can imagine the C++ class where you have some local field and also the process function. So for example, if you send a message to another actor, your message first comes into this mailbox, and this actor process messages one by one. And this is very typical execution model, and but we sort of extended this to the more like a distributed computing setting, and with PGAS, and just give you some very, very simple examples so that you can get some intuition about how a FA-BSP model works with a typical but eccentric graph algorithm. And again, so this is super simple program where we only have 3 vertices, B0, B1, B2, and suppose that these vertices are distributed by the 1D cyclic fashion, where you do the modulo operation to identify which P owns which vertices. In this case, the P0 owns the 2 vertices, whereas the P1 owns just 1 vertices. And so the code on the bottom is that our FA-BSP version, where the blue part is again local computation, so there's no communication, and so you just iterate over your local data structure. Maybe in this case you iterate over the 2 local vertices on P0, whereas the P1 iterate over its local vertices B1. And at some point you initiate some asynchronous send, and maybe you might want to propagate some value to the another vertices through the edges, something like that. And so so you can just imagine such operation. So you just invoke the send operation to some specific destination PE, and this is a synchronous call. And at some point, runtime is sort of the switching between the back and forth between main part and this message processing part. So the sort of these blue part and the red part is interlinked. And at some point, this message handler is invoked, and then there's some local data within that actor is updated. So yeah, we found that this model works pretty well with different graph and the non-graph algorithm. And also I know there are several people already talks about the conveyor library conveyor library, and which actually one of the source of the performance improvement. So we are able to implement our FA-BSP version of the different algorithms like veil kernels, and also we have been working on the IRPAR project where we accelerate lots of the real-world regular applications, and we already are able to get a very nice result. And some of them, Youssef published the ISC paper on the Jakarta, and also another co-author, Shub, was able to publish their. This. Someone confirms that. No, one of their co-author, Shub, was also able to publish their paper on the inference mathematician at this year SC, and Youssef, he did the two graph algorithm using our model, and he got the CC Grid Best Scale Challenge Award for 2 consecutive years. So essentially, we are super confident with the expressiveness of our FA-BSP model, and also that it gives you a really nice performance improvement over the state-of-the-art implementation. And if you are very, very interested in this approach, we already have some website on that. And if you go to the etsy-actor.com, you'll see lots of information like how to use our container or how to use our model on the conventional supercomputer like Parameter at NASC or PACE GT cluster. And if you're interested, please visit our website. Okay, this is a very, very the background. And here we sort of try to extend our execution model to more like a multi-threading setting. So recall that previously we sort of doing the single-threaded execution model where each actor is single-threaded, and you need to do some explicit communication between actor to do active messages. And actually, one good point about this is that actually no atomics are required because again, so this is single-threaded, and you send a message to another actor, and the receiver just processes the messages one by one. So there's no atomics required. Actually, this is another source of the performance improvement we got in our previous work. And but maybe one potential drawback would be, since you can imagine that there's super huge supercomputer where there's millions of core, and each since we only create one actor per thread, so you have to create millions of actors and communicating with each other. That might sort of increase the total number of the inter-actor communication. So maybe one thing we could try is that is it worth doing the multi-thread setting per actor? And this might sort of reduce the number of inter-actor communication, but at the same time, of course, since now we have multiple threads within the actor, we definitely need to do some mutual exclusion or something like that. That might sort of degrade the performance as well. So this is more like an early study as to whether this multi-threading model is worth doing. So, and I just use distributed triangle counting to verify that this hypothesis is correct or not. And currently, we are focusing on parallelizing the message handler within the actor, and we came up with 2 approaches. And the left-hand side is blocking messages, where so every time you receive a message, the message handler is called, and we use the HCLib finish construct, which is very similar to extend finish construct, or more like a very open MP barrier or something like that, which waits on the completion of all the tasks created within this finish. And so that every time you receive a message and you create, maybe you can create as many asynchronous as possible, but just waits until all the asynchronous tasks are completed. And this sort of complies with the actor model decision model because the actor model enforce you to process the messages one by one. So, but as long as you do the synchronization within the message handler, it's still valid actor program. And one problem is that so in our regular, FA-BSP application, this message handler is called a million times. So the question is that is it just okay to do this synchronization million times or something like that, because this adds more overhead. And another approach is non-blocking messages. So essentially, we just remove this finish from this message handler, and which makes this message handling more asynchronous. Every time you receive a message, you create an asynchronous task, and at the very end, these tasks are synchronized. But as you receive the messages, you create a asynchronous message, and this actually can improve the throughput, and also maybe it may give a more work steering opportunity. But now the problem is that you create a lot of asynchronous tasks, and the programmer has to deal with more the data laces because there are multiple tasks running on the multiple core, and which may touch the same shared memory location. So so this might be the one of the challenging issue. And also again, so this actually breaks the actor model. And actually, these two approaches are sort of inspired by the VIVEKFEST paper, perhaps Ustra paper. And Sham, the past PhD student, has been reading that direction within our shared memory setting. And here, I just gonna exploring this with a distributed setting.
Does this mean that on the right there's an implicit finish and the whole?
Right. So after everything, actually, there's one big finish. And which waits on everything. So this asynchronous task was synchronized when that finish is called, yes. Okay, and I'm gonna very briefly talk about our runtime implementation. And so like I mentioned earlier, so our runtime pretty much depend on the conveyor library, which is a message aggregation library. And but now we have multiple threads per actor, and one problem is that actually conveyor API is not thread safe. So our current solution is that we just assign the communication task exclusively to the communication worker. Actually, the HCLib has the capability of importing the task at a specific location. And I think Extend also had some concept called place or something like that. And so you can just create a communication task and let the communication worker execute that communication task so that we can avoid that thread safe problem. And moving on to the more empirical performance studies. And this is sort of very busy slide, but essentially we are talking about our very basic version of the triangle counting. And I think you can just focus on this figure in the middle, where suppose the one actor has this vertex I, and it iterates over its neighbor. In this case, you have two neighbors, J and K, and their local operation. But then the question is that there's any H in the J and K, and essentially we're gonna send the active message to the PE that owns this vertex J and see if there's any edge, and just increment the counter if there's such an edge. And we do this we do this in a very asynchronous way, and finally do the all reduce to count the global triangle number. And so this is a experiment setup, and we use the Georgia Tech phase cluster, and that are actually connected with the InfiniBand. And we use the scale 16 and 20 RMAT graph. And for experimental variants, we tried two versions. And one is a very basic version, baseline version, and where we actually send just one pair of the integer 6040 to the other actor, whereas the another version, chunked version, was essentially intended to create a much bigger messages so that the message handler can have much more parallelism. So actually, in this case, we created the 624 pairs of the integer, and this is the chunk. This is called chunked version, and this is a very early result on the PSGT cluster. And as I said earlier, so that we use two graphs, two input graphs. The left-hand side is the scale 16 graph, and the right-hand side is the scale 20 graph. And here, y-axis is absolute performance number, which means the lower is better. And we have multiple variants. The baseline is the original time counting implementation with one worker. And orange one is the chunked version. Actually, what's interesting that the chunking already gives you some nice performance improvement. This is sort of the user level message aggregation. So we have multiple layers of the message aggregation. So the runtime do the message aggregation, but also the user does the message aggregation. And what's surprising is that the doing chunking already gives you the very nice performance improvement. And when it comes to the multi-worker version, and you may not be see the significant difference, but the trend here is that this chunked two-worker non-working version is the fastest, and the chunked one-worker version is in the middle. And when you do the blocking version, which if you remember that in the process function we have a finish construct which waits on the completion of all the asynchronous within the message handler. So actually, this is the slowest among three versions. So at least we are able to see that the chunked version and with two worker is better than the chunked version with one worker. And but another interesting thing is that so remember that this message handler is called million times. And actually, we realized that when we increase the number of worker, it sort of adds more overhead of creating the new task and the new worker or something like that, and which actually degrade the performance a lot. And actually, this two-worker setting is one of the best setting, which gives you the best performance. And that concludes our talk. And we are able to enable the user-level asynchronous tasking in the FA-BSP model. And we saw some performance improvement, but we also admit that we have to do very, very careful hand optimization to get the performance improvement over the baseline. So but at least we're glad that we saw some performance improvement. And we're going to try more evaluation with different applications. And maybe one of the interesting future work would be like, so depending on the input graph, so that we saw the scenario where that the P0 has so many incoming messages, whereas the others not having so many incoming messages. So maybe we could do some heterogeneous or non-uniform actor where maybe actor 0 has, say, 10 threads or 100 threads, whereas the other actor only has a single thread, something like that. And that might sort of resolve the load balance issues or something like that. And we're going to look to work on that in the future. And this is just an acknowledgement to the IRPR. And the next slide is the most important slide. And I just going to say the huge thanks to our big boss, Professor VIVEKFEST and Habanero Mafia. And I actually really agree with what Michael said earlier, where the Vivek is very like our grandfather or grandmother or something like that. And he's always very, very friendly and treat me as a very independent researcher, and we really appreciate that. And I just created some pile of some photos, and actually this is the Georgia Tech mascot, Buzz, who is sort of uploading the accomplishment. So that's pretty much it. I'm very happy to take questions.
Mm-hmm. And then I noticed that the difference between blocking and non-blocking is not really very big for two workers.
Right.
So does this mean that we should pick, if they're so close, we should pick the one that's easier to program, which I think must be blocking?
Exactly, right. So I agree. So like I mentioned earlier, so it was sort of very hard to get the performance improvement with non-blocking version. But again, like you said, maybe there's not super huge difference. So right, you're right. So we maybe want to stick with the yeah, and maybe ultimately actually we still we actually the default version, one-thread version is still our default, and we sort of pushing that direction. But for some application which may require the multi-threading, that this is more like yes, the optimization for very specific application, and so but yes, we are sort of exploring the scenario where this multi-threading setting is beneficial, and yeah, we are still exploring the
domain specific.
yeah, right.
Thank you.
Thank you.